Today's lesson is going to focus on Bohr's model of the atom and flame tests, which are a simple way to prove Bohr's model and prove the existence of energy levels. Back in the 18th century, a lot of chemists were studying compounds that were burning with colored flames, and they were confused by this and a bit intrigued because most items burn with an orange flame. So they were trying to figure out what were causing these different colors. And at the time, they were aware that different colors correspond to different energies on the electromagnetic spectrum of visible light. So, this electromagnetic spectrum is shown here at the top of your screen. This should look familiar to you from grade 10 optics and when you were studying light energy. So, what they were doing was they were getting different colors of light to appear. And if you look down here, you'll see some neon signs as an example. And then what they did is they looked at those colors through a spectrum. So, through a prism. And a prism is just a piece of glass that will separate light into the different colors that make it up. So we know that white light is made up of all the colors of the spectrum, but sometimes something like yellow is maybe made up of, not just yellow light, but maybe a little bit of blue, maybe a little bit of red, depending on the tone or the shade or the hue of the color. It's made up of more than one distinct color. So, what they do is when they look at the emission spectra through a prism, they see these bands of light that you see here under the emission line spectrum image. And those are called atomic line spectra. And as it says there, they are also unique to every element that we have on the periodic table. So, over the years, chemists have taken these samples of different elements, they've applied a lot of energy to them and they've put them in the gas phase. And then when they look at them through a prism, they notice that there are these different colors of lines that are emitted as a result. So here are some examples of four elements. So there's carbon, oxygen, nitrogen, iron. And again, what's happening here is they've taken samples of these elements, they have heated them up into the gas phase so that they are glowing. And they're glowing a certain color. And then when they look at it through a spectra, or a spectrophotometer that has a prism in it, they notice these bands of colored lines. And these lines are very unique for each element. So iron always looks, the same with that, grouping of purple and some greens and some oranges. Nitrogen doesn't have as many lines, but it always looks the same. And that's how they are identifiable. So, what Bohr did is Bohr studied hydrogen gas, and he took the gas and he applied a lot of energy to it. And then he looked at what was the emission spectrum of the gas as he applied a lot of energy to it. And he noticed these four distinct colors of light coming up in the spectrum. So, what he knew was that different colors of light had different energies associated with him. And if we look in the paragraph here, it says he postulated that an electron can have only specific energy values in an atom, which are called energy levels. So, Bohr knew that there were electrons in the atom, but these colors of light were indicating that those electrons were maybe jumping around within the atom. And depending on their placement, where they jumped to, that would correspond to different energies because there were different colors being produced. So we know that red is associated with low energy, purple is associated with high energy, and so any color that we saw in between led Bohr to believe that electrons were possibly sitting in different spots within the atom with different potential energies. So, why are they called energy levels? So, Bohr believed that the energy levels for electrons contained potential energy. He also stated that the further away from the nucleus, the more potential energy the electrons have. And this makes perfect sense. The nucleus is positively charged. It makes sense that our electrons want to be as close to the nucleus as possible, but they are not. If they were, the whole atom would implode and we would have no matter existing on Earth at all. So instead, he suggested that these electrons were held at distinct areas or locations away from the nucleus. And how do these electrons move between energy levels? This is what he was seeing when he saw different colors of light. It says by gaining the right amount of energy, an electron can move or undergo a transition from one energy level to the next. So we can explain this on this next slide. So let's say an electron absorbs outside energy and it moves to a higher energy level. So in order to do this, you'd have to apply a lot of outside energy. Okay, so just heating it up or turning on the furnace, okay, to try to excite an electron is not going to do it. You need a lot of outside energy, and what will happen is, and this in this image here, you'll see that. Get my pointer if I can. Oh, sorry, I cannot. So we'll just take a look here. You see there's a purple arrow that says energy in. That purple arrow is indicating energy that the electron is absorbing, and then it jumps up, if you follow the purple arrow, to a second energy level. We call that the excited state. The electron will not sit there forever, okay? It will come back down to its original position. So if we look at the top of the image there, we see like the yellow electron and we see the green arrow indicating that the electron is moving back to its original position, which we call a ground state. When it does that, it has to release any energy that it absorbed initially. And so it will release energy that corresponds to how much energy it needed to jump energy levels. If it only jumped one energy level, didn't need a whole lot of energy, so it releases a low amount of energy on the return. If it jumped 2 or 3 or 4 energy levels, that means it needed a lot of initial energy to jump that far away. Then it's going to release a lot of energy on the way back to the ground state, and that energy will correspond to a certain color. So if we come back here to our points, we already talked about the excited state. It says the electron is now further from its original position and undergoes a transition back to its original lower energy level, which we call a ground state. In that process, the electron loses energy that it had originally absorbed. And when it loses that energy, it's going to release it as a photon of light. Okay, so a particle that behaves like a wave. And that photon of light, the color that we see, corresponds to the amount of energy that was released. If it was a low amount of energy, we're going to see red or orange. If it was a higher amount of energy, we're going to see, blue, green, or purple. The energy difference between the high energy level and the low energy level is related to the frequency or color of the light emitted. And this is what we see here again. So here's a nice image, and we see high energy is associated with the purple side of light. Low energy is associated with the red side of light. Many different elements burn different colors. So again, it's unique to all of them. And you see here some of these colors correspond to certain elements when we excite them, and we excite those electrons. And these colors are all used in fireworks. So when they make fireworks, they will put in certain elements such as copper or maybe potassium. And when the firework is lit or ignited, the colors of the fireworks that you see will be based on some of these elements that always give off certain colors of light when the electrons are excited.